So now we're going to look at a required practical, and it's the combustion of alcohols. So the first thing you do is measure out 100 centimeters cubed of water, and you put this into a measuring cylinder and then pour it into a thin copper container, which is placed on top of a tripod stand. And we use a windscreen to try and keep as much heat in the area as possible. And then the second thing you do is record the initial temperature using a thermometer. So you record the initial temperature of the water. And then number 3, you weigh a methanol lamp, which we will be lighting, and that will be our burning fuel. And we place this under the metal container and light it. And then we stir the water in the metal container with a thermometer, and this ensures that the heat is uniform throughout the water. And when the temperature of the water increases by a certain amount that you decide beforehand, so in this example we have 30 degrees Celsius, we take out the flame and then we record the temperature that the water is at. We then reweigh the lamp, and this should give us the mass that has been burnt. So in order to find the enthalpy change, we first use Q equals mc delta T. And M here in this case is the amount of water that has been heated. So we have 100 centimeters cubed of water, and 100 centimeters cubed is equal to 1 gram. And because this is needed in grams, so we have Q equals 100, and then you times it by the specific heat capacity of water, not alcohol. It would be of the water. So Q is always to do with water, or whatever you are. What is the thing that's the energy, the heat energy is being risen or decreased. So in most cases, Q will be to do with water. So then we'd have 4.18, which you don't need to remember, but that's the specific heat capacity of water. And then you'd have delta T, and delta T in this case would be 30 degrees Celsius, because that's how much it's changed by. So that comes to a certain amount, and then we convert it to kilojoules. And then we can find the enthalpy change, which is delta H, and that equals Q over moles. And this moles here, that is the moles of the alcohol. So in this case, it's methanol. So that would be CH3OH. So the moles of CH3OH equals the mass of it divided by the MR. So it would be the mass that's been burnt, so the reweighed mass minus the original mass, and then divided by the MR of CH3OH. And then we have the moles. So then we just use this equation, delta H equals, and then use this thing that we've got in kilojoules and divide it by moles. And we have to remember that because this is exothermic, because heat is being lost from the reactants, but it's heating up the surroundings, this has to be a negative, which means that this delta H at the end will be negative. So now we're going to look at a question. Feel free to pause the video and try it out for yourself first. So 500 centimeters cubed of 1 mole per decimeters cubed of hydrochloric acid was added to 500 centimeters cubed of 1 mole per decimeter cubed of sodium hydroxide. The temperature rose by 6.8 degrees Celsius. Calculate the enthalpy of neutralization for this reaction. Assume the density of the solution is 1 gram per centimeters cubed, and that the specific heat capacity of the solution is 4.18. So first what I would do is to calculate the moles of hydrochloric acid and sodium hydroxide to see what actually reacts. So the moles of hydrochloric acid equals the mass over the molar mass. So actually, for this one, we use concentration times volume because we're not given the mass. So we have concentration times volume, but these have to have the same units. So we're going to use decimeters cubed. So we need to convert this to decimeters cubed. And the way we do that is divide it by 1,000 or times 10 by -3. And then we times it by the 1 mole per decimeters cubed. And this gives us 500 times 10 to the -3. And then we do the same for the sodium hydroxide. And this is actually exactly the same. 500 times 10 to the -3. And then the next step is to look at the equation. So when we mix sodium hydroxide and hydrochloric acid together, we form salt and water because this is an acid and alkali reaction. So we form the salt NaCl, sodium chloride, plus water. And this is already balanced, so this is the equation. And then we look at the ratio of sodium hydroxide to hydrochloric acid reacting. And as we can see, it's just a 1-to-1 ratio. So it's 1-to-1 ratio, and that's for the moles. So if we looked at hydrochloric acid and we've got 500 times 10 to the -3, then that means that 500 times 10 to the -3 moles of hydrochloric acid would react with 500 times 10 to the -3 moles of sodium hydroxide. And we have that here. So that tells us that none of the reagents are in excess, so both of them react until they've both finished reacting, there's nothing left. So that actually doesn't make a difference. So we know that 500 times 10 to the -3 moles is what's been reacted. So now we use our Q equals mc delta T equation. And then we need to remember the units. So this is grams. This is already given to us, and this is either degrees Celsius or Kelvin, it doesn't matter. And this will come out in joules. So now we just plug in the values. So the mass here is the mass of the solution. So the solution would just be 500 centimeters cubed plus another 500 centimeters cubed. So that would be 1,000 grams. And then you times it by the specific heat capacity, which is 4.18. And also a centimeters cubed is equivalent to a gram. And then you times that by the 6.8 degrees rise. So for that, you should get 28,420 joules, which is equivalent to 28.42 kilojoules. So that's the heat energy that's been given out. And now to find the enthalpy of neutralization, which is just the enthalpy change, is we use delta H equals Q over moles. So here for the moles, it actually doesn't matter which moles we use because we actually use the same amount of both. So we do 28.42 divided by 500 times 10 to the -3. And that gives us minus 568.4 because the minus here signifies that it's an exothermic reaction, so we definitely need to remember that. And we round this to minus 568 kilojoules per mole. And the rounding is also really important because you can get marks deducted from not rounding correctly. So in the questions, we can see that lots of these figures are to 3 significant figures. So that's what gives us a clue to what to round this to. So we've also rounded this to 3 significant figures. Hi everyone, thanks so much for joining me for this video. We're going to look at some harder questions for the topic of calorimetry now. So the first question says, the enthalpy of combustion of propan-1-ol is minus 2020 kilojoules per mole. 0.6 grams of propan-1-ol is burnt and used to heat 200 grams of water in a calorimeter. The starting temperature of water is 20.3 degrees and the specific heat capacity of water is 4.18. How much heat is released when 0.6 grams of propan-1-ol is burnt? Now, the first thing we do is we write out the 2 equations we know. So we know Q equals mc delta T, and we also know delta H equals Q over moles. And now we have a look at what information we have. So here we have delta H, and this is the mass of the propan-1-ol. This is our M, because you have to remember that for this equation, this always talks about the water or whatever's being heated. So the M here will be this 200 grams and not the 0.6 grams of propan-1-ol. The starting temperature is 20.3 degrees. And we've also got C here, which is the specific heat capacity. So from this, we can tell that we can't use this straight away because what we're trying to find is the delta T. And so we use this equation first. And we have the delta H, and we can find the moles by using the mass here and dividing it by the MR. So if we rearrange this formula to get Q as the subject, then we can hopefully use it in this equation, which has been, if we rearrange it to find delta T, then we'll be able to find it. So Q equals delta H times by moles. Delta H we know is minus 2020, and then you times by the moles, which is mass over the MR. So we have 0.600, and then the MR, which is, we've got 1, 2, 3 carbons, so that'll be 3 times 12, and then you plus 3 hydrogens, 2 hydrogens, 2 hydrogens, and another hydrogen, so that's plus 8. And then we also plus the oxygen, which is 16. And this gives us a total of minus 20.2 kilojoules. And then we remember that in this equation, we have to have Q in joules. So we have to convert this back into joules. So that's minus 20,200 joules. And then we rearrange this formula. So we get delta T equals Q over mc. And then plug in all the values we know. So we have the Q. It doesn't really matter now to include the negative because that's just telling us that heat was lost to heat up the surroundings. So we can ignore that. So we get the 20,200. And then you divide by, this is now the mass of the water, so 200. And then you times it by 4.18 because that's the specific heat capacity of water. And then you get 24.1 degrees Celsius. So this is the change in temperature because that's what delta T means. And so in order to find the theoretical temperature of the water at the end of the experiment, we then add this value onto 20.3 because it's exothermic, so the temperature is increased. So this is the answer for A. And then for B, we do 20.3, which is the starting temperature of the water. And then you add on the 24.1 because it's exothermic. And then you get 44.5 degrees Celsius. And one thing to note here is that when we calculated this, it came out as a decimal. So it came out as 24 point and then a few decimal places. We rounded it to 24.1 for A because everything else is in 3 significant figures. So this should be in 3 significant figures. But then when we use it for other calculations, we need to use the actual figure. So we don't round it to 24.1, it'll be a decimal again. So that's how we get 44.5 degrees after rounding. And that's also to 3 significant figures. And then for C, is the final temperature likely to be higher or lower than this theoretical answer? The answer is that it will likely be lower. And this is because lots of the heat will actually be lost to the air or also to the container that it was in. So heat loss makes the experiment less accurate. So it goes to the air, or you could say it goes to the container, but basically it just doesn't heat up the water, because it's not only just heating up the water, it's heating up other stuff as well. So that means that the actual temperature of the water at the end won't be as high as 44.5 degrees. So this second question is a bit more involved, but feel free to pause the video and to try it first. So 50 centimeters cubed of 0.1 molar of silver nitrate solution was put in a calorimeter and 0.2 grams of zinc powder was added. The temperature of the solution rose by 4.3 degrees. First work out which reagent was in excess and then calculate the enthalpy change for the reaction per mole of zinc. So assume that the density of the solution is 1 gram per centimeters cubed and that the specific heat capacity of the solution is 4.18. And we ignore the heat capacity of the metals just for simplicity. So first what I do is work out how many moles of silver nitrate solution and how many moles of zinc we have. So the moles of silver nitrate, now they only give concentration and volume, so we can't use the mass over MR formula. We have to use concentration times volume. And it's normally volume in dm cubed and concentration in moles per dm cubed. So we're going to convert this 50 centimeters cubed to decimeters cubed. And the way we do that is divide it by 1,000 or times 10 to the minus 3. And then we times it by the 0.1. And this gives us 5 times 10 to the minus 3 moles. And then I'm going to work out the moles of zinc. And now we can use the mass over MR because we're only given the mass. So we have 0.2 over the MR of zinc is 65.4. And that gives us 3.06 times 10 to the minus 3 moles. And now we look at the equation and we look at the ratio. So the equation tells us that 2 moles of silver nitrate react with 1 mole of zinc. So if we first look at the silver nitrate, that means that if we have 5 times 10 to the minus 3, then that should react with half the amount of this number of moles of zinc, because it's a 2-to-1 ratio. So then it would react with 2.5 times 10 to the minus 3 of zinc. And if we looked at it the other way around, so if we start off with the zinc, if we have 3.06 times 10 to the minus 3 of zinc, then that would react with double that amount. So that would react with 6.12 times 10 to the minus 3 of the silver nitrate. So now we've written the ratios out, we can see that if we go with this method, we don't have enough of the silver nitrate because we've only got 5 times 10 to the minus 3. So we can't do this. So this must be happening. And so this also tells us is in excess, because only 2.5 times 10 to the minus 3 moles of it reacts, but we've got 3.06 times 10 to the minus 3, so we've got more than what there is to react with silver nitrate, so there's some left at the end. So now we write out the equation that we know, so Q equals mc delta T, and plug in the numbers. So mass here would be the mass of the solution that's been heated. So we've got 50 centimeters cubed of it, and that's equivalent to 50 grams. And then we multiply it by the specific heat capacity of the solution, which is 4.18. And then multiply it by the change in temperature. And it says here that the temperature of the solution rose by 4.3 degrees. And this comes to a certain amount of joules, which I've converted to kilojoules. So it's 0.8987 kilojoules. And now we use the delta H formula. So we've got delta H over Q over moles. And here, the question asks for per mole of zinc that reacts. So this is going to be mole of zinc that reacts. So we'll have 0.8987 over the moles of zinc which have reacted, which is the 2.5 times 10 to the minus 3. And then that comes to minus 359.48 kilojoules per mole. And now we look back at the question and have a look to see how many decimal places or significant figures they've rounded everything to. And it looks like they've all got 2 significant figures. So then we round this to minus 360 kilojoules per mole. And I've added in the minus here because it's an exothermic reaction. Technically, you can add the minus here, but so that's better if you think you'll forget it. But adding at the end is fine as well, as long as it's in the final answer.